Hello all and welcome to Intro to Filters. This will be a multi-part video and it will end up covering labs 6 through 9 for if you're following along with the course. So what is a filter? A filter allows for specific frequencies to be passed through while stopping other ones. Ideally, it would appear as a perfect transmission line in the pass band, letting all signal through, and ideally it would also appear as an infinite attenuator in the stop band, getting rid of all unwanted signals, and then at the same time have no phase distortion, meaning that all different frequencies are affected the same in its phase delay. So we just covered impedance matching. So if we think about it, a matched network allows for full transmission, and an unmatched network causes reflection, which impedes transmission. Could we take advantage of this process and use it to, at certain frequencies, have a well-matched network and at other frequencies have a poorly matched network? And the answer is yes. That is at the core of what we're doing in filter design. So what type of filters can we make? Well, there's four main types. We can make a low pass, which allow frequencies below our cutoff frequency through, high pass, which let frequencies above our cutoff frequency through, band pass, which allow a certain bandwidth of frequencies through, and band stop, which prevents a specific range of frequencies from coming through. Some terminology we're going to need for this set of lectures is omega c, which is your cutoff frequency. Now remember, omega c is 2 pi f, 2 pi times the cutoff frequency. N, which is the order, which tells you how quickly the filter attenuates after your cutoff frequency. Pass band, which is the frequency band at which your filter allows frequencies through. The stop band, which is the band at which your filter does not allow frequencies through. Rejection, which is your S21 measurement outside of your pass band. Insertion loss, which is your S21 measurement inside your pass band. Bandwidth, which refers to mostly band pass and band stop filters, and that's the amount of band that it does let through. Quality factor, which is a way to measure the efficiency of your filter, looking at its losses and how narrow banded it is. Selectivity and roll-off are ways to describe how quickly your filter attenuates the frequencies after your cutoff frequency. And group delay, which looks at the phase and how it is affected throughout your filter. We're going to start with low-pass filters, and in this set of slides, we are just going to look at the lumped element design. So if we think about the case where your frequency is much greater than your cutoff frequency, so let's bring everything to an extreme here. We know the impedance of an inductor is j omega L, so as omega approaches infinity, higher and higher frequencies, the impedance of an inductor will become infinite, so it will look like an open. Conversely, the impedance of a capacitor, which is 1 over j omega c, will tend towards 0 as omega tends towards infinity, and that will look like a short. So as you can see in the second diagram here, we have something that will not pass frequencies through for frequencies much, much greater than omega c. Taken to the other extreme, if we look at frequencies much, much below omega c, so DC, we can see that the impedance of the inductor will tend towards 0, looking like a short, and the impedance of a capacitor will tend towards infinity, looking like an open. So in these two extremes, we have no frequencies coming through much greater than our cutoff frequency, and all the frequencies coming through much below our cutoff frequency, effectively making a low pass filter. So let's look more specifically at the lumped element filter. Now, a lumped element filter consists of series inductors and shunt capacitors. Each element adds another order to the filter. So as shown here, these are just second order filters as they have two elements, one inductor, one capacitor. They're designed using polynomials. Some of you may remember this from your basic circuit theory, such as Butterworth or Chebyshev. So the pros of using a lumped element filter is that they're a simple design. You'll see in a second as we do the design, the math is pretty simple. There's not a lot to it. They use basic circuit theory, so those who don't even have an RF background at all could conceivably go through these as they're done to be electrically small, making them good at low frequencies where quarter wavelengths or any multiple of wavelengths start to become very large. These will be very small still as they are electrically small circuits. The cons, though, are because you're using discrete elements, they do become lossy. They require assembly, unlike something that uses just transmission lines, and they are frequency limited. As we mentioned, they're good at low frequencies. However, we want these to be electrically small, so as we get to higher frequencies, it becomes more and more difficult to get the circuit in the size that we need it. Additionally, certain components like inductors do not perform very well at high frequencies as they hit their self-resonant frequency. There are 3 types of polynomials we'll be using for this course. The Butterworth polynomial, sometimes called maximally flat or binomial, will give you a flat response in the passband and an all-right attenuation rate. The Chebyshev polynomial will give you a better attenuation rate at the cost of your passband having a ripple inside of it. There are 2 different design variants in the text. One is the 3 dB equal ripple, and the other is the 0.5 dB equal ripple. Additionally, there's the maximally flat time delay, and this one focuses on any effects to your phase, reducing dispersion in your signal. I will now go over the design process with the Butterworth. However, you can use the same design process for all 3 different polynomial types. I will just be including the charts and the tables for the Butterworth in this example. So your first step is to obtain the cutoff frequency and the required rejection, and then use the chart on the right here to take the ratio of the frequency at which you want your rejection to your cutoff frequency, take the absolute value, subtract 1, and then look at the attenuation that you want at that frequency. So if I wanted to have at a ratio of 2 or 3, 2 minus 1, so I'd look here, and then I want an attenuation of 30, I'd come up to 30 and see that the next curve up, the one that will achieve that attenuation or greater, is going to be a 4th order filter. Once you've used that and you know your filter, use the second table here to go to the 4th order filter, and these are the coefficients of your polynomial. Now you'll notice for Butterworth, the g of n plus 1 is always 1. G of n plus 1 describes your load impedance. For Butterworth, that is always 1 and it will always renormalize to 50. However, for filters like the Chebyshev, some orders do not end in 1, and that would give you an unmatched filter. So it might be advantageous to bump it up to the next order if you find yourself in that scenario. But once you get your G values, you can add them to your circuit. Now there's 2 different options with the low pass. You can do inductor first or capacitor first. They work the same. They do just give you different numbers though. It could be valuable to look for both and figure out which one gives you more realistic circuit values. Once you've picked your design and you have your G values, you have to renormalize them. So for all inductors, you take that characteristic impedance, you multiply it by whatever G value you have for that inductor, and divide by omega C. For the capacitor, it's very similar. You take that G value and you divide by your characteristic impedance times omega C. Now, one important thing to remember here is omega C being your cutoff frequency is not F, it is 2 pi F. Students often forget to divide by 2 pi when performing this conversion, and will get the wrong numbers because of that. So let's give an example of a design process. Say you've been told to create a low-pass filter with a cutoff frequency at 1 gigahertz, and it has 20 dB of attenuation at 2 gigahertz. So first we have to look at our table, and we know that 2 over 1 is 2, minus 1 is 1. So we'll look at 1, and we decided we wanted 20 dB of attenuation at that frequency. So we go to 20 dB. Now we just are above n equals 3. So we won't achieve 20 dB of attenuation with a 3rd order filter, so we have to bump up to a 4th order filter. So once we've selected the order of our filter, we then need to go to the chart for a 4th order filter and grab all the G values. And I have them listed here. Next, we need to select the topology. As I said earlier, there's two different options, and it may be advantageous to explore both and see which one gives the most realistic values. However, for this example, we're just going to go with capacitor first. So now that we've selected the topology, we can assign the G values to the capacitors and the inductors, and then we have to use our equations to renormalize them to our frequency and our characteristic impedance. And when we plug all these in, we get the values here. And plugging them into our circuit in ADS, you can see the circuit that we get and the response that we get. Looking at S21, we can see a flat pass band with a minus 3 dB cutoff frequency at 1 gigahertz. And we can see as it crosses over and begins to attenuate, and we have the design requirement to be under 20 dB at 2 gigahertz, which we have achieved. So this is a successful design. Now you might notice that the values of our capacitors and our inductors are starting to become quite small. For the 1 gigahertz design, they were still within reasonable values. However, if you look at our equations, as omega c increases, these values are only going to get smaller. At about 2 to 3 gigahertz, they start to become small enough that realistically we cannot use a lumped element design anymore, as the values would be too small to realize the components. Another option is distributed elements, which use techniques involving transmission line to create your filter elements. We will look at that in more detail next week.